Welcome to the first introductory lecture of numerical and machine learning methods for differential equations. I'm your lecturer, John Butler. My email is john.s.butler, and you can have a look at my research and some of my other teaching at my website, johnsbutler.netlify.app. Now, just a bit about me. I did a PhD in computational fluid dynamics, which is numerical methods for partial differential equations, where I designed something called an adaptive mesh or an adaptive grid to solve fluid flow problems. From there, I moved to the Max Planck for biological cybernetics, where I investigated walking and driving using robotics and virtual reality. Some differential equations came into that, but not much. Then I moved to Albert Einstein College of Medicine, where I did a lot of work on people with autism and people with Niemann-Pick and neurotypicals and aging population, where I recorded brain signals on the scalp, electrical signals of the brain. That requires some differential equations. The Laplacian is most commonly used because it converts, but also there are other differential equations that come in. Then I moved back to Ireland and worked in movement disorders. But in the background, throughout that time, I was developing my knowledge of different methods. And one method that started popping up, even back in 2007, was machine learning methods. Initially not for differential equations, but they're more and more becoming vogue. And that kind of links to, in a vague fashion, is I did a lot of numerical methods in my PhD, and since then I'm slowly moving towards machine learning methods. So a bit about the module itself. The aim of the module is to equip the learner with the knowledge necessary to implement computational techniques related to finite difference methods and machine learning methods for differential equations. Pretty much what we said, but it's that link of the classical, which is finite difference, to the more modern methods of machine learning. The course is divided in two parts. The first part of the module, the learner will be introduced to theory and practice numerical integration of ordinary differential equation with initial conditions. It might seem a very sudden shift. In the second part of the module, we introduce the application of machine learning methods to estimate solution of linear and non-linear ordinary differential equations. We'll be doing a bit of Python as well. Software tools, Python, will be used to implement these methods. It might seem that it's a very aggressive change in the middle, a very sudden change. But hopefully, as we go through the course, you can see actually it's a very reasonable progression. The learning outcomes: derive and apply a range of finite difference methods for solving differential equations for initial and boundary value problems. Critically review the stability, consistency, convergence properties of various numerical integration schemes for different practical problems. Interrogate the difference between various numerical methods for integration of differential equations, and evaluate the conditions under which they are an appropriate choice. Formulate and apply machine learning methods to approximate the solution of differential equations. And once again, throughout there's numerical methods. This terminology, stability, consistency, and convergence, is a very numerical terminology, numerical analysis that is. But actually, we will talk a bit about that when we start talking about machine learning methods. The course has two components: 40% continuous assessment, which is a case study, and 60% a final exam. Once again, we start with our initial value problems, and we start at the very beginning with the Euler method. That leads into Taylor methods, and then the most popular method used, which is the run-coda. And they're all called one-step methods because they use one step back in time to predict the future. Then we use multi-step methods, which are the two Adams method, Bashford and Moulton. These use multiple time steps in the past to predict the next step in the future, taking the dynamics of the differential equation. Then we'll briefly touch on some finite difference methods just to build up a matrix. But the one we're most interested in is the shooting methods. And that is actually the kind of breakpoint. The shooting methods we introduce link very nicely with the neural networks. Shooting methods have to learn something about the equation it's trying to solve, and that's exactly what a neural network does. So that's how they link together. Some references for the course. Steve Brunton's book, which is also available online, Data Driven, Steve Brunton and Nathan Kutz. Data Driven Science and Engineering is excellent. It's in the library, but also there are copies of it online as well. It's probably better for the second half of the course. A classical numerical analysis book is a first course numerical analysis for differential equation. It covers a lot of what we do. The Burden and Ferris book, also very nice for numerical methods. And in a more general, to think about differential equations, because that's what we deal with, the Stephen Strogatz book, really, it covers everything you need to know about differential equations, but not the numerics. The first three are numerical machine learning books, while the last one is about the differential equation. I'll also be supplementing some academic papers as well, where some of the proofs that we're going to be doing in the second half will be coming from. Just on a broader thing, to put a larger zoom out on why it's important, how these methods might be used in different ways. Here are some popular books. Hannah Fry is a great book that introduced both statistics and machine learning. And it's very readable and entertaining. Stephen Strogat's book really links into why we care about dynamical systems in the real world, what they can be used for. For me, once again, the machine learning side and the stuff I really care about is very nicely covered in Grace Lindsay's book, Models of the Mind, How Physics, Engineering, and Mathematics Have Shaped Our Understanding of the Brain. I'm a computational neuroscientist, is my preference, but also it gets you thinking about the link between maths and other areas, as well as machine learning and so forth. Melanie Mitchell's book, Artificial Intelligence, A Guide to Thinking Humans, is a wonderfully readable book about the history and the future of machine learning, or AI. These terms are quite interchangeable. I'm sure people in the field really care, but I would consider less so. Then lastly, Perry Zern and Danny Bass's book, Curious Minds, The Power of Connection. That's just an interesting book about how things are connected, how to think about things. It's a fun read. It's quite erudite, I'd say. Then on an audio side, some podcasts that actually overlap with this. Now, pretty much anything is a dedication to Stephen Strogatz. So The Joy of Y and The Joy of X are both podcasts by Stephen Strogatz, where he interviews scientists. They both give a wonderful overview of some of the interesting maths out there. There are a couple of seasons of Deep Mind, the podcast by Hannah Fry, and she's interviewing people about the future and the past of AI. And then in the similar way, Brain Inspired covers the mathematics, the neuroscience of AI as well. And that's interviews with researchers. More Irish related is The Function Room by Colm O'Regan, where Colm O'Regan, who's a comedian, interviews mathematicians from Ireland, actually, and around the world about what they do. And so hopefully it'll give you an interest in some of that. Now, some of the resources that are free online and are excellent. Once again, it's the Stephen Strogatz Show. His video lectures on nonlinear dynamical systems, that'll be very useful for biomaths and for this, well worth watching. Steve Brunton, as I said, his book is Dynamical Systems with Machine Learning, and the videos corresponding with are on his YouTube channel. His videos are some of the most professional you'll see out there. He's a wonderful communicator. Similarly, Jason Bramberg, who's also, I think, might have done his PhD with someone adjacent to Steve Brunton. has some lovely videos in the same vein about dynamical systems and data-driven. And he's also written a book that he's made available online called Data-Driven Methods for Dynamical System, A New Perspective on Old Problems. Lastly, Neuromatch Academy is a summer school I work with, and we've produced materials specifically on deep learning. Now, this is my third different word for machine learning, or artificial intelligence, or deep learning. They are Python notebooks that will start you in the right direction when we're building our neural networks later on in the course. If you're looking for a nice night in, but also feel like you want to be studying, these are some great movies that consider dynamical systems and machine learning. So War Games is the most obvious and classic, but they all have elements of this. And then more apocalyptically pushed is the more recent movies. But really, the debate is, and I think at the end of the course, hopefully this isn't a debate, are machines sentient? No, they learn a curve. So, as I said, we're going to cover all this over the next 13 weeks. And hopefully you'll find some interesting parts along the way.